Training procedures. Improving convergence. Gradient descent has various advantages. It is simple. It is log, namely the change in a way it uses only the values of the presynaptic and postsynaptic units, and the arrow suitably backpropagated. When online training is used, it does not need to store the training set. It can adapt as the task to be learned changes. Because of these reasons, it can be and is implemented in hardware. But by itself, gradient descent converges slowly. When learning time is important, one can use more sophisticated optimization methods. You can check Batiti in 1992, Bishop 1995 discusses in detail the application of conjugate gradient and second-order methods to the training of multilayer perceptrons. However, there are two frequently used simple techniques that improve the performance of the gradient descent considerably, making gradient-based methods feasible in real applications. Momentum. Let us say Wi is any weight in a multi-layer perceptron in a new layer, including the biases at each parameter update. Successive delta Wi to the t values may be so different that large oscillations may occur and slow convergence. T is the time index, that is the epoch number in a batch learning and the iteration number in online learning. The idea is to take a running average by incorporating the previous update in the current change as if there is a momentum due to previous updates. That is, delta Wi to the t equals to minus eta times delta e to the t differentiated by delta Wi plus alpha times delta Wi to the t minus 1. Alpha is generally taken between 0.5 and 1.0. This approach is especially useful when online learning is used, where as a result we get an effect of averaging and smooth the trajectory during convergence. The disadvantage is that the past delta Wi to the t minus 1 values should be stored in extra memory. Adaptive learning rate. In gradient descent, the learning vector eta determines the magnitude of change to be made in the parameter. It is generally taken between 0.0 and 1.0, mostly less than or equals to 0.2. It can be made adaptive for faster convergence, where it is kept large when learning takes place and is decreased when learning slows down. That is, delta eta equals to plus a if e to the t plus tau is less than e to the t, and the delta eta is equals to minus b times eta otherwise. Thus, we increase eta by a constant amount if the error on the training set decreases, and decrease it geometrically if it increases. Because E may oscillate from one epoch to another, it is a better idea to take the average of the past few epochs as e to the t. Overtraining. A multi-layer perceptron with d inputs, h hidden units, and k outputs has h times d plus 1 weights in the first layer and k times h plus 1 weights in the second layer. Both the space and time complexity of an MLP is big O of h times k plus d. When E denotes the number of training epochs, training time complexity is big O of E times h times k plus d. In an application, d and k are predefined and h is the parameter that we play with to tune the complexity of the model. We know from previous chapters that an overcomplex model memorizes the noise in the training set and does not generalize to the validation set. For example, we have previously seen this phenomena in the case of polynomial regression, where we noticed that in the presence of noise or small samples, increasing the polynomial order leads to worse generalization. Similarly, in an MLP, when the number of hidden units is large, the generalization accuracy deteriorates, see figure 11.12, and the bias variance dilemma also holds for the MLP, as it does for any statistical estimator. A similar behavior happens when training is continued too long, as more training epochs are made. The error on the training set decreases, but the error on the validation set starts to increase beyond a certain point. See figure 11.13. Remember that initially all the weights are close to zero and thus have little effect. As training continues, the most important weights start moving away from zero and are utilized. But if training is continued further on to get less and less error on the training set, almost all weights are updated away from zero and effectively becomes parameters. Thus, as training continues, it is as if new parameters are added to the system, increasing the complexity and leading to poor generalization. Learning should be stopped early to alleviate this problem of overtraining. The optimal point to stop training and the optimal number of hidden units is determined through cross-validation, which involves testing the network's performance on the validation data unseen during training. Because of the non-linearity, the error function has many minima, and a gradient descent converges to the nearest minima. To be able to assess expected error, the same network is trained a number of times starting from different initial weight values, and the average of the validation error is computed. Structuring the network. In some applications, we may believe that the input has a local structure. For example, in vision, we know that nearby pixels are correlated and there are local features like edges and corners. An object, for example, a handwritten digit, may be defined as a combination of such primitives. Similarly, in speech, locality is in time and inputs close in time can be grouped as speech primitives. By combining these primitives, longer utterances, for example, speech phenomes, may be defined. In such a case, when designing the MLP, hidden units are not connected to all input units because not all inputs are correlated. Instead, we define hidden units that define a window over the input space and are connected to only a small local subset of the inputs. This decreases the number of connections and therefore the number of free parameters. We can repeat this in successive layers where each layer is connected to a small number of local units below and checks for a more complicated feature by combining the features below in a larger part of the input space until we get to the output layer. See figure 11.14. For example, the input may be pixels. By looking at pixels, the first hidden layer units may learn to check for edges of various orientations. Then, by combining edges, the second hidden layer units can learn to check for combinations of edges. For example, arcs, corners, line ends, and then combining them in upper layers. The units can look for semicircles, rectangles, or in the case of a face recognition application, eyes, mouth, and so forth. This is the example of a hierarchical cone where features get more complex, abstract, and fewer in number as we go up the network until we get to classes. In such a case, we can further reduce the number of parameters by weight sharing. Taking the example of visual recognition again, we can see that when we look for features like oriented edges, they may be present in different parts of the input space. So instead of defining independent hidden units learning different features in different parts of the input space, we can have copies of the same hidden units looking at different parts of the input space. See figure 11.15. During learning, we calculate the gradient by taking different inputs, then we average these up and make a single update. This implies a single parameter that defines the weight on multiple connections. Also, because the update on the weight is based on gradients over several inputs, it is as if the training set is effectively multiplied. Hints. The knowledge of local structure allows us to pre-structure the multi-layer network, and with weight sharing it has fewer parameters. The alternative of an MLP with completely connected layers has no such structure and is more difficult to train. Knowledge of any sort related to the application should be built into the network structure whenever possible. These are called hints and are the properties of the target function that are known to us independent of the training examples. In image recognition, there are invariance hints. The identity of an object does not change when it is rotated, translated, or scaled. See figure 11.16. Hints are auxiliary information that can be used to guide the learning process and are especially useful when the training set is limited. There are different ways in which hints can be used. Figure 11.16. The identity of the object does not change when it is translated, rotated, or scaled. Note that this may not always be true and may be true up to a point. B and Q are rotated versions of each other. These are hints that can be incorporated into the learning process to make learning easier. One hints can be used to create the virtual examples. For example, knowing that the object is invariant to scale from a given training example, we can generate multiple copies at different scales and add them to the training set with the same label. This has the advantage that we increase the training set and do not need to modify the learner in any way. The problem may be that too many examples may be needed for the learner to learn the invariance. The invariance may be implemented as a pre-processing stage. For example, optical character readers have a pre-processing stage where the input character image is centered and normalized for size and slant. This is the easiest solution when it is possible. 3. The hint may be incorporated into the network structure. Local structure and weight sharing, which we saw in section 11.8.3, is one example where we get invariance to small translations and rotations. 4. The hint may also be incorporated by modifying the arrow function. Let us say we know that x and x prime are the same from the application's point of view, where x prime may be a virtual example of x. That is, f of x equals to f of x prime, when f of x is the function we would like to approximate. Let us denote by g of x conditioning on theta our approximation function, for example in MLP where theta are its weights. Then for all such pairs, x, x prime, we define the penalty function EH equals to the square of g of x conditioning on theta minus g of x prime conditioning on theta, and add it as an extra term to the usual arrow function. E prime equals to E plus lambda h times EH. This is a penalty, penalizing the cases where our predictions do not obey the hint, and lambda h is the weight of such a penalty. Another example is the approximation hint. Let us say that for x, we do not know the exact value f of x, but we know that it is in the interval, the closed interval between ax and bx. Then our added penalty term is EH equals to 0 if g of x conditioning on theta is in the closed interval between ax and bs, and the EH is equals to the square of g of x minus ax if g of x conditioning on theta is less than ax, and the E of h is equals to g of x minus bx, then to the square if g of x conditioning on theta is greater than bx. So this is similar to the arrow function used in a support vector regression in section 13.10, which tolerates small approximation errors. Still another example is the tangent prop. This is promoted by Simard et al. In 1992, where the transformation against which we are defining the hint, for example, rotation by an angle, is modeled by a function. The usual arrow function is modified by adding another term so as to allow parameters to move along this line of transformation without changing the arrow.